Endomorphin 2 is a peptide with the amino acid sequence shown. Each amino acid is represented by a 3-letter abbreviation. Figure 2 shows part of the structure of endomorphin 2, showing the tire-pro-phe part of the molecule. NH2 at the end of the amino acid sequence of endomorphin 2 shows that the terminal functional group is an amide and not an acid. Complete the structure of endomorphin 2. Okay, so what we need to do is this is quite tricky. I'm going to do some highlighting. Obviously, you can't do this in the exam, but we need to remember that each of these is a peptide or an amide bond. So we've got the first one between the C double bond O and the N here. So that means that if we're looking at it and we want to see where our TYR is, it's everything that is in here. This is all our first amino acid. Okay, I'm just going to remove that. Then we've got our pro being, if we find the next peptide link here, then proline is the next section. So I'm just going to remove my colouring in. I'm just going to keep the highlighting of the peptide links. So then we're connecting the next amino acid here must be phenylalanine, and so we're going to connect it again. So what we actually have to draw here is the same thing from the last connection, because there's 2 phenylalanines in a row. So I've got an NH, and then it goes to a CH, which goes to a CH2, which goes to a benzene ring. And then it comes down here to a C with a double bond O. It says the end group is an NH2 rather than the end of the carboxylic acid. So I have to finish that off with the NH2 at the end. Use the structure in figure 2 to draw the skeletal formula of proline. So we need to go back and find proline was the second amino acid along. So proline is this bit here. So I need to copy that and complete and make sure I do it all as skeletal. So lose some of those atoms that are shown out. So if I just copy it to start off with, I can always do some rubbing out. You can use pencil in the exam and rub it out, and then go over it in pen at the end. We've got a C with a double bond O, and then this is connecting to our 2 peptide links. So when we make a peptide chain, we lose the hydrogen off a nitrogen, and we lose the OH group off the carboxylic acid group. So this is nearly the right answer, but we need to be careful because it said skeletal formula. So this carbon here can't be shown. So we want to come out of there, tidy that up a bit, and have our double bond O and our single bond OH. We show this hydrogen on the nitrogen and the hydrogen on the O because they're not on carbons. A student hydrolyzes a sample of endomorphin 2 to break it down into its constituent amino acids. Student analyzes the resulting mixture by thin layer chromatography. State the reagent needed for hydrolysis. Well, we'll need fairly concentrated hydrochloric acid. It needs to be a strong acid, and we're going to reflux it for quite a long time to break those peptide links. Figure 3 shows the apparatus used for TLC. There's a piece of apparatus missing. The omission will result in an inaccurate chromatogram. State and explain the piece of apparatus that is needed. Well, you can see straight away we need to cover this with a lid. And the reason we need to do that is to prevent evaporation of the solvent from the beaker So we want to prevent evaporation of the solvent from the beaker and the plate, and ensure that the atmosphere in the beaker is saturated with solvent. All of these ensure good separation of the amino acids. Without them, the amino acids won't separate well and they won't move up the plate. State why the amino acids separate. This is all to do with the key to any type of chromatography. There is a difference in their solubility in the moving phase and their retentions. They all have a different balance between their solubility in the moving phase and their retention to the stationary phase. This is the basic principle of all forms of chromatography. When the solvent has risen up the TLC plate, the student removes the plate from the beaker and sprays it with a developing agent. Figure 4 shows the results. Name the developing agent. Well, for amino acids, the developing agent is called ninhydrin. And the reason we need it is that amino acids are colourless ninhydrin makes them visible. The last bit of the question says determine the RF for TYR. Now, I'm going to be using this ruler on the iPad. You may get different values but for your readings, but your RF value should be the same because it's a proportionality. So although my screen is a different size to your piece of paper and my ruler isn't necessarily measuring in centimetres, you would get the same you'll get the same ratio, so you get the same RF value. So on mine, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.25 as our bottom line. So 11.25 for the solvent. And then if I scroll along, TYR 1, 2, 3, 4, 5, 6.15 for the spot. And so my value is coming up as 0.55. So anything within the region of 0.54, 53 to 55 was acceptable. Just gonna scroll down. And so any value, again, it will depend on the measurements that you make, but you should have a value between 0.53 and 0.55. Anything in this range will be acceptable.